Okay, so some folks asked me if I would work some of the angular momentum or angular motion problems that I had assigned for the homework, to give you an example of sort of what I think of as like key ideas. So the first one I picked is this, the sphere and the mass that are rolling down an inclined plane. And we're trying to figure out what the speed, which one will have the greater speed at the bottom of the ramp. And so the reason I picked this problem to work is that it's an energy problem. So what we're thinking about here is how energy changes from the top of the ramp to the bottom of the ramp, and how that's different for something that just slides versus something that rolls. So since it's an energy problem, I think about what's in my system. And so I'm going to have, in either case, I'm going to have the object. So let's just label it like that. And I'm going to have the Earth. And I'm actually going to just leave the inclined plane out of my system because it's not particularly doing anything, because there's no friction or anything that's relevant to this problem. So I'm just not going to worry about it. Okay, so then in both cases, energy then is conserved as they move from the top of the ramp to the bottom of the ramp. And the energy that they have at the top, both of them is potential energy. And because I'll set 0 to be at the bottom of the ramp, that just means that at the bottom of the ramp, then all of the energy has gone from potential energy to kinetic energy. So this potential energy at the top and kinetic energy at the bottom. Okay, so potential energy, the form for that then is mgh. And the kinetic energy total, I know, is 1/2 mv squared for the linear portions and 1/2 I omega squared for the nonlinear portions. And the block won't have the I omega squared portion because that's the rotational piece. But for the sake of working this problem out, let's just keep it there for the moment, and then we'll see how that plays out. So let's start by doing, working on the rotational, the sphere piece. Let's make this a little smaller. Move it up, back up here. Okay. So let's start with working on the sphere is what it is. Okay, so for the sphere then, what I get is mgh is equal to 1/2 mv squared plus the I for a sphere is 2/5. Let me write this over. 2/5 mr squared. So I get 1/2 times 2/5 mr squared. And I get that I just by looking it up. I look it up on a table. Times omega squared. But I also know that omega is equal to v over r. So let me just plug that in, that omega is v over r squared. Right? So if I keep working this down, then what I get is 1/2 mv squared plus 2/10 mv squared. And then I get v squared, sorry, that was an r, mr squared, v squared over r squared. And so the r's cancel out. And so what I get is 1/2 plus 2/10. 1/2 is 5/10. So I get 5/10 plus 2/10 is 7/10 mv squared is equal to mgh. So now I have m on both sides, and so the v squared here for the sphere is equal to 10/7 gh. Okay, so this is at the bottom of the ramp. The speed will be 10/7 times gh. Okay, so that's the sphere. Okay, now let's think about what the block looks like. So the block still has mgh plus 1/2, mgh equals 1/2 mv squared. And then the other term, the rotational term, is 0 because this thing's just going to slide down the ramp, so I don't have to worry about that. So then if I solve this guy for the v squared, mgh equals 1/2 mv squared. Again, the masses cancel out, and so what I get is v squared is equal to 2gh. Okay, so if I compare these two then, the question I'm asking is 10 sevenths smaller or bigger than 2? Well, 10 sevenths is equal to 1 and 2 sevenths. So it is less than 2. So the velocity of the block is greater than the velocity of the sphere at the bottom. Okay. So the other problem I chose to do for you is the flywheel. So we're thinking about a flywheel that has a particular moment of inertia, and the question is, what's the average power? So this is an energy question again. You need to spin it up from rest to an angular velocity of 90 radians per second in 34 seconds. The reason I chose this one is actually because you have to do a lot of different pieces here to think through this one. Okay, so what we know then, or at least in my version of the problem, we know that the moment of inertia for this thing is 2.1 kilogram meters squared. We know that its original angular velocity was 0, and it gets to an angular velocity of 90 radians per second, and it takes it 34 seconds to do that. Okay, so what we're doing here then is we have this disk, and it's starting from rest, and we're starting to spin it, and we're spinning it over a period of time, and we're asking, what do you have to do in order to get it to spin that fast? Okay, so in thinking about a power question then, we know power is equal to the change in energy over the change in time. Right, so the kind of energy that we're talking about here is rotational kinetic energy, because this thing is spinning around. Right, so power then for this problem will be the change in the kinetic energy over the time. And the change in the kinetic energy is started at rest. So the change in kinetic energy is just the kinetic energy final over the time. Okay, so knowing all of this then, we can start by saying, well, what will be the kinetic energy once this thing is rotating at its full speed? So kinetic energy is equal to 1/2 m, oops, not m, 1/2 I omega squared, right? So I put in 1/2 times my 2.1 kilogram meters squared times my final omega here, because I'm doing the final kinetic energy, is 90 radians per second squared. So I put this into my calculator, and what I find is that the kinetic energy is 17010 kilogram meters squared over second squared. Okay, so this is the kinetic energy. Okay, so then in order to find the power then, what I need to do is take this number. So I take the change in kinetic energy over the time, and that will give me, sorry there, I lost, I hit the button accidentally. But so what I did in the interim there is I put the change in kinetic energy over the time, and that's what gives me the power, and the time there is 34 seconds. So the second part of this question then is asking me about what the torque required is, right? And I know a couple of things about torque. The first thing I know about torque is that it's equal to F times R perpendicular. I also know that torque is similar to the force, and so in this similar way, we can talk about the net torque as having an I alpha relationship. And so if this is the only thing that I'm seeing happening here is that there's a torque being exerted and it makes this thing rotate, then I can probably just use this form because the force is not something that I know or that I'm being asked about. Okay, so what is alpha then? Alpha is our change in omega over our change in time. Right, so this is changing, we're assuming in a constant way. And so alpha then is just going to be that 90 radians per second minus 0 radians per second, because that's the original, over the time it took is 34 seconds, right? And so if I have torque is equal to I alpha, then what I'm really just saying is the I is 2.1 kilogram meters squared times the alpha is that 90 radians per second over 34 seconds. And so I find then that the torque is equal to 5.56 Newton meters. Okay, and so that's all there is to this problem.